Are you ready to learn something fascinating today?
Yes.
Okay, great. We're going to learn indeed something really fascinating. We're going to talk about scaling arguments to solve a particular heat transfer problem. As I said, we're going to deal with the semi-infinite wall. Our system is not going to be a slab, but our system is going to be infinitely long solid. Okay, we call it semi-infinite wall. The reason it's semi, not infinite, it's because it's not extending in both directions, but it's extending in one direction infinitely. Okay, and the wall is kept at a temperature Ts, surface temperature, and initially the wall is at the temperature T0. So you can think of this temperature at here initially. It's at T0. Okay, you can think of it as, like, for example, Earth being at a certain temperature at like in the start of the summer, and the sun rays are actually heating up the surface, and then the Earth is actually heating up, and so on and so forth. And this is a perfect transient problem, similar to the ones that we solved before. But our boundary conditions are extremely different than what we had before, right? First of all, I only have one surface. I have one surface boundary, right? I can say it's like x is equal to 0, the t is equal to ts, but I don't have the other boundary. And I don't have a characteristic length. So that's one of the peculiarities of this problem, which first seems like a challenge or a difficulty, but then it looks like something very important for us to simplify our problem. Okay, so let's say this is at t is equal to 0 second, and then you can have different temperature profiles. As time goes, you can have T1, T2, and so on. Okay, okay, so what is going to be my differential equation? The partial differential equation. Now, do I need to do the shell balance again and do this like Qx in, Qx out, and so on? I don't need to do it, right? Because I already did it for the slab, and I'm pretty sure that I'm going to get the same answer for this. I'm going to have exactly the same partial differential equation. Del squared t over del x squared is equal to 1 over alpha del t over del t, where alpha is thermal diffusivity, which is K over rho Cp. K solid, rho solid, Cp solid. Okay. If this is Earth, this is K is the thermal conductivity of the Earth, rho is the density of the Earth, Cp is the heat capacity of the Earth, and so on. Now, the first question is the following. We had non-dimensionalized this equation for the previous problems, but now, can we non-dimensionalize this partial differential equation? It looks like no, right? Seems no. Because although I have a characteristic temperature, I am given, or we are given, let's be more inclusive, although we are given a characteristic temperature, which is Ts, we do not have any characteristic length or time. We do not have any characteristic length or time. Think about it for a moment. Now, do I really not have any length scale? Well, maybe you can say if I'm given some time, if I'm only considering, for example, heat transfer within 10 seconds or maybe 1 year, then I can come up with some made up characteristic length depending on how deep the temperature profile penetrates, right? You can think of a penetration length as a function of time. So you can say, for example, assume you're given some waiting time or maximum time, for example, Tmax, right? And then you can come up with some penetration depth, Xmax, which relates to the Tmax, right? You can say for example, this is Tmax. Let's imagine, although the system can actually evolve until infinity, you can just stop at some point, and this can be your Xmax, right? And you can do some sort of scaling analysis, like for example, you can say, let me define X over X max, T over T max, and so on, right? You can say define X over X max is equal to psi, and T over T max is equal to T tilde. Okay. Now, if I non-dimensionalize using these two, and also theta is equal to T over Ts, for example, the surface temperature, then you would get something like del squared theta over del psi squared 1 over x max squared is equal to, on the right hand side, 1 over alpha 1 over T max del T over del T tilde. Okay. And you would get something like del squared theta over del psi squared is equal to x max squared over alpha T max. Okay. Del T over del, oops, this is del theta. There you go. Okay. Okay, so far so good. So what does this say? Imagine that, like, the quantities theta is in the order of 1. The psi is in the order of 1. Okay, imagine that you just want to find out the temperature profile somewhere around this region, where your psi, which is x over x max, is somewhat comparable with 1. It might not need to be equal to 1. It might be maybe 0.1, but it's not 0.00001. So it's not very different from 1. This is like some sort of scaling argument. And let's assume that T tilde is also in the range of, in the order of 1. Okay, so we can say that del squared theta over del psi squared and del theta over del T tilde are in the same order of magnitude. Same order of magnitude, right? So why am I actually doing this? Because I got a quantity which relates the x max to t max, and it tells me that this thing must be in the order of 1. Okay? Thus, x max square over alpha t max is going to be in the order of 1. Meaning that as time goes, this quantity is actually does not change at all. It does not go to infinity. It does not go to 0. It actually stays in the same order of magnitude, right? So this means that if after, like, if you can find, for example, x max square is like increasing quadratically with time, then you would find this not equal to 1. Maybe you're going to find it sometime later, you're going to find it 1,000, and then sometime later you're going to find it million, and so on, which is actually in contradiction with this order of magnitude estimate. So basically, you can say that no matter how much time elapsed, you can think of this x max square over t max within the same order of magnitude. So you can say, in other words, x max square is in the same order of magnitude with alpha t max. Or in other words, x max is in the same order of magnitude square root of alpha t max. Okay. Or you can think of it as like x reference. You can take a reference point and like declare, you can say, okay, if I get close enough to this temperature, I call this as the penetration depth. Or you can call it like a penetration depth is going to scale with the square root of alpha times t, right? Good. So you can think of it as like a reference temperature, or sorry, reference time and reference position. Okay, so what does it mean? It means that after like 100 seconds, if it penetrates like 10 meters, then that means after 10,000 seconds, it's going to penetrate 100 meters. So this is a very nice relation about this. So the order of magnitude estimation gave us this relation. But we still want to solve this desperately. Would like to solve this differential equation exactly. To have an idea about the temperature profile. So, okay, this equation gives me an idea, a rough idea about how the x or how the penetration thickness changes with time. But I want to find out the temperature profile as well, not only the penetration depth. Okay. This also taught us the fact that, unlike the previous problems, in which there is a natural length scale, in this case, the length scale itself depends on time. It's changing with time, meaning that as time increases, the length up to which there is a temperature disturbance increases, and it's actually related to the time with this relation. Okay. Now, let's solve this equation exactly. And what we're going to learn, what we're going to do and learn is what's called as a scaling argument. And which is something fascinating. Okay, let's have a look at our system and our equations. Okay, now our system is like this, Let's call this the temperature. Let's call this the X. And your temperature profile might be after some time. Something like this, right? And we ask the following question. What happens if we zoom into the system? What happens if we zoom into the system? Please pay attention here. I mean, this is something phenomenal. This is something great. And I recommend you to pay utmost attention here. Now, what do I mean when I say zoom into the system? I mean the following. When I use my iPad, I can just zoom in pretty easily, right? And I can find it, like see the details much easier. But mathematically, what does it correspond to? It corresponds to the following. It corresponds to changing the units. Imagine that you have the units of meters. Now, imagine you want to see the units of centimeters or maybe nanometers. Okay, or maybe just centimeters. We don't need to exaggerate the case, but you can have something like this, right? Correct? For the same time. It might look a little different. Mathematically, what does it correspond to? It means multiplication by some unit conversion factor, right? Instead of using x, using a times x. For example, instead of using 1 meters, using 100 centimeters. So it's like a unit conversion, right? But I would like to call it like a scaling, like you scale in, like zoom in and zoom out. But how about the time? Oh, okay, I can also zoom in the time and zoom out the time. I can work with, for example, nanoseconds instead of seconds, right? Let's actually use b times t instead of t, okay? But what is it going to tell us? Believe me, it's going to give us something really remarkable. Let's have a look at the equations for this. Del squared t over del x squared is equal to 1 over alpha del t over del t, correct? And what I claim is the following. I should have exactly the same equation, at least up to some multiplication factor. I should have the same equation for the zoomed in case or the zoomed out case. And I want to replace all the x's by a times x, all the t's by b times t. So replace x's by ax. It should hold. T's by bt's. It should hold. Although you're changing the units, the alpha is going to have a different units, but that's okay. Let's see what's going to happen at this moment. I'm going to have 1 over a squared del squared t over del x squared, right? Because I have I have double derivative is equal to 1 over alpha, 1 over b. I have one derivative of t, so I have 1b del t over del t. Okay. So I zoomed in my position, I zoomed in my time, I found a different equation, I found the following. Del squared t over del x squared is equal to a squared, over b times 1 over alpha del t over del t. Now I say that I wish, or we wish, to have exactly the same partial differential equation. Okay. So that we know that we have the same solution. Let's say partial differential equation and boundary conditions. So that we know that we have the same solution for the original and the scaled case. Okay. So, but that means the following. Let us take a squared over b equal to 0. Oh, sorry, what is that? A squared over b is equal to 1. So let's take this one so that I recover my original partial differential equation. How about the boundary conditions? The boundary conditions were originally at x is equal to 0, t is equal to ts. And at x goes to infinity, t is equal to t0, or time goes to infinity, right? But not time goes to infinity. At time is equal to 0 initially, t is equal to t0. So basically either x approaches infinity or time approaches 0, you have temperature equal to the initial temperature, T0. Okay? And you can say that my boundary condition would change with the scaling argument as at ax is equal to 0, which means x is equal to 0. It's not affected by the scaling, you can see t is equal to ts. And at ax goes to infinity, meaning that x goes to infinity, t is equal to t0. And bt is equal to 0 means t is equal to 0. T is equal to t0. Okay, so basically I have exactly the same boundary conditions. But let's take a squared over b equal to 1, meaning that let's take b equals to a squared. In other words, for this equation, del square, or maybe for our zooming, convert the x to ax, but t to not bt, but a squared t. Right? And what do we see? We get exactly the same equation and same boundary conditions, so we get exactly the same solution, right? Solution remains the same. Wow. Something fascinating. Now you're gonna, if you're not surprised, you're gonna see in a moment that this is a remarkable result we're gonna make use of, which is gonna give us a very important information about the solution. Now, is everybody convinced that we get exactly the same function t is equal to f x comma t for the two cases? Because we have this, I repeat it again. If you take the scaling factor of t to be a squared and the scaling factor of x to be a, then what happens is you get exactly the same differential equation with exactly the same boundary condition, meaning that you exactly have the same function, the same solution, the function that solves the equation. So the solution in the two cases are the same. What does it mean? It means the following. The solution, f, or you can think of it as like theta, or t maybe, for x comma t is exactly the same as the solution at ax comma a squared t. Okay, it means the following. The temperature at 100 meters after 1 second is exactly the same as the temperature at 200 meters and 4 seconds. Okay, it's basically the same result as we found here. The penetration depth scales with the square root of the time, and it's basically a supporting fact that we find the same temperature when you actually multiply the x by a, but t by the square of a. Okay, if you use square of the scaling factor of x for the t, then you get the same temperature. Now you can say, okay, so what? What are we gonna? How are we gonna make use of it? Now, here is the argument. Now you have the same solution, right? This means the following. If you define a quantity which is called like x squared over t, for example, like look at the following quantity. Sorry, let me write down this. Imagine that you are basically dividing the t to the x squared over t, right? For this case, the x squared over t is x squared over t. For this case, the x squared over t is ax squared over a squared t, which is basically identical to a squared x squared over a squared t, right? Which after the cancellation of a squares, you get x squared over t. Basically, that means the following. When the temperatures are equal to each other, this x squared over t is identical for the two cases. So this actually gives us the following clue. It says, oh, maybe this temperature is just a function of x squared over t, right? Because it's the x squared over t, which is the same in two cases. When the x squared over t does not change, the function does not change. So that means it's only a function of x squared over t. You can say the following. Okay, maybe I can combine all the x dependency in x squared over t, and then maybe it's a function of t as well. But then as you can see here, when you change the t from t to a squared t, this would change if it were a function of time, but it's not changing still. So that means it's definitely, certainly, and exactly a function of x squared over t. Is this part clear for everybody? This is very important. Okay, if anything is unclear about the fact that the temperature must be a function of x squared over t, then please ask. Okay, so then what are we going to do? We're going to actually define a quantity which is called eta. Okay, and I'm not going to define it as x squared over t, but I'm going to define it something similar, which is x over 2 times square root of alpha t, for the reasons that's going to be clear. So this is basically the some constant times the square root of x squared over t. And I say that if this is a function of x squared over t, this must be also a function of the theta, because, sorry, eta, because eta is a function of x squared over t. Okay. Good. I mean, in other words, anything you write as a function of x squared over t, you can write it as a function of eta as well. For example, if your function is x squared over t to the 4th, then you can basically write it as 2 square root of alpha eta to the power of 8, right? So you can always relate one to the other. You don't need to write it as separately as function of x and t. Okay, good. Okay, this is gonna simplify our situation to extremely much. And what we're gonna do is the following: we are gonna replace okay, let's go with the 3rd page. Sorry. So what we have found so far is our equation is del square t over del x is equal to 1 over alpha del t over del t, and we use change of variables. Eta is equal to x over 2 times square root of alpha t. Okay, and we found that t is a function of eta only. I mean, it's not a function of eta and t or x together. Okay, so we found that you can actually write down t as a function of eta. Now let's find out del t over del x. We know that the t changes with eta. You can write it del t over del eta, but it's not partial derivative anymore. It's total derivative because it changes with eta but nothing else. It's not going to be a partial derivative, but the eta changes partially with x, right? That's how you write the derivative of t with respect to x from the chain rule. Okay, this is called the chain rule. Okay, and from here we get dt over d eta and del eta over del x from this definition here. You have 1 over 2 square root of alpha t. Okay, and del square t over del x squared similarly is del over del x, del t over del x, and del t over del x we already found, dt over d eta, 1 over 2 square root of alpha t, and del over del x is again d over d eta times the 1 over 2 square root of alpha t. And this is constant. You can take it out of the parentheses. Oh, sorry, it's not. Is it constant? I guess it's not. It's not a constant, right? Okay. It's not a constant. Okay, let's see. Oh, okay. So here's what we do here. Basically, instead of doing this first, we're gonna use a trick here. Let's take this out of the parentheses first before we do anything else, because we know that the time is not a function of position. So you can basically write down del over del x, del t over dt over d eta. Now this is 1 over 2 square root of alpha t. Now I can actually expand this because this is a function of eta only. D over d eta times d eta over dx, which is again another factor of 2 square root of alpha t. So you get square root. Let me write it here. The second derivative with respect to eta times 1 over 4 alpha t. Okay, this is del squared t over del x squared. This is the left-hand side of this this equation, right? Now let's write down del t over del t. Del t over del t is equal to dt over d eta again, and del eta over del t, which is dt over d eta times del eta over del t is the derivative of this with respect to time. So basically the constant terms are x over 2 square root of alpha, and the derivative of 1 over square root of t is, since it was t to the minus 1/2, you get the minus 1/2 here, and then you subtract 1 from negative 1/2 for the exponent. So it looks like negative 1 over 2 times t to the 3 over 2. Okay, and then from here, okay, so okay, yeah. So let's actually place these two terms in our original equation. Left-hand side is going to be d squared t over d, let's say, inserting these into our original partial differential equation. We get eta squared 1 over 4 alpha t is equal to dt over d eta okay, and we get x, so minus x over 4 square root of alpha. So there is 1 t here, square root of alpha t. Okay, good. Yep. And then we get rid of the 4's, t's, right? Okay, there's 1 alpha appearing. Oh, there's 1 alpha in the equation already, right? Is equal to 1 over alpha. We already have that alpha in the equation. Yeah, there you go. and the alphas cancel. And what we get is the following. D squared t over d eta squared is equal to minus, you can multiply by 2 and divide by 2, and the term becomes equal to eta, so minus 2 eta dt over d eta. So this is the equation that we find. We can celebrate it because it is an ordinary differential equation, which is simpler to solve compared to original partial differential equation, right? And I need the boundary conditions for this. We said that at x is equal to 0, t is equal to ts, which corresponds to the boundary condition of at eta is equal to 0, because for x is equal to 0, eta is equal to 0, t is equal to ts. And at x is equal to infinity, t goes to t0, which corresponds to eta going to infinity, t goes to t0. Similarly, for t going to 0, t is equal to t0. It's basically the same, it corresponds to the same boundary condition. So the two boundary conditions gave us the same boundary condition, which makes sense because going from partial differential equation to ordinary differential equation, you need two boundary conditions right now, not three, because you have one variable for which the t depends on. So these are your boundary conditions. For the ordinary differential equation. Okay. Now, how are we going to solve this equation? We are going to basically have a look at this. dt over d eta. You can actually declare it to be some function of eta so that you only have one derivative, like first derivative instead of two derivatives, right? So let's call g eta to be equal to dt over d eta. It's a function of eta again. And our ordinary differential equation becomes the first derivative of g eta is equal to minus 2 eta g eta. Let's collect all the g etas and etas on one side, on separate sides. dg over g is equal to minus 2 eta d eta. And you can take the integral both sides. From eta is equal to 0. Okay, how shall we do this? Let's not do definite integral, but let's do indefinite integral. And you get logarithm of g, or logarithm of g eta, is equal to negative eta squared plus c. And then from here, you find g eta is equal to exponential minus eta squared times exponential c, but the exponential c, you can call it another constant, which is c prime. Okay, And since g eta we define as dt over d theta, right? So you can yeah, you can actually plug it there. Get the following. Integral. Oops. Yeah. First, let's do step by step. dt over d eta is equal to c prime exponential minus eta squared. Let's multiply both sides by d eta and take the integral. Okay. And then we know that at eta is equal to 0. Let's use the eta as both the dummy variable and the constant number. For chemical engineering students should be fine. Maybe it might be bothering for math students, but let's do it this way. Probably you know what I mean here when I say eta is equal to 0, and when I use the same eta here. But ideally, you should use a different variable in both cases. Okay, going from eta 0 to any eta, and T is Ts, the surface temperature, to any T. Okay. From here, you find T minus Ts is equal to C prime times 0 to eta exponential minus eta squared d eta. Okay, so we're almost done. We're getting close. Now, another boundary condition we're going to use at eta goes to infinity. We know that T goes to, and I regret that I didn't use theta instead of T, but that should be okay. So we can actually go back to the theta instead of T. Yeah, I'm going to write it in a second. So T goes to T0. Okay. From here, you get basically, you get the following. T0 minus Ts is equal to C prime integral from 0 to infinity exponential minus eta squared d eta. Just because of the time does not permit us, I'm not going to show this, but one can show that although we don't have an analytical solution for this integral, we know that from 0 to infinity, we know the value of this integral. You can use either integral tables or there is a trick basically for those who are interested. Maybe I can actually show you during extra help hours, but you should get square root of pi over 2 for this integral. Okay. Okay. So C prime comes out to be equal to 2 over square root of pi T0 minus Ts. And if we replace it in this equation, let's say star, plugging in equation star, we get T minus Ts divided by T0 minus Ts is equal to 2 over square root of pi, integral from 0 to eta, exponential minus eta squared d eta. Okay. Good. Okay, so there is a name, special name for this function. This entire thing, this function is called error function of eta. Okay. Some properties, error function ERF x. One, the error function of 0 is strictly 0 because, as you can see, if you plug in 0 here from 0 to 0, you get 0 value for the integral, right? If the integral has the same boundaries at the 2 points, you get 0. The second property is error function infinity is equal to, if this goes to infinity, we know that this entire thing goes to square root of pi over 2, so after the cancellations, you get 1. Error function infinity is 1. It basically looks like the following. It starts from 0, goes up to 1, asymptotically. I guess it should be something like this, as far as I know. I should check. Let me check really quick. Error function graph. Okay. Oh yeah, it's like this. The error function looks like exactly how I showed you. Good. But oh no, sorry. It's basically it's basically something like this, but we are gonna take from 0 to infinity, so it should look like the following. Okay, there you go. 1, 0, x, error function x. Schematically, it looks like this. It approaches 1. Okay, there you go. So we found the temperature distribution for this case. Do you have any questions? We still have 10 minutes. Okay, no? You don't have any question?
On exam and quizzes, will you give us how to solve like the error function? Will you give us like a table to plug in values?
Oh yeah, I guess you have it in your textbook. Let me check really quick. It's a great question. Let's see, error function. Let's see the index. Error function 285. Okay, do you have your calculators? Maybe in your calculators you might have the error function. If your calculators can take integrals, you can calculate it. There is also like approximate estimation of it in your textbook in the transition between pages 285 to 286, which corresponds to our discussions that we did. So basically, you can find it like a 0.5% error. You can find it. Okay, so I recommend you to have a look at that. And I believe your calculators, you can you can do the integration, so you can actually calculate it. Okay. Any other questions? No. Okay, let's do in 9 minutes. Let's do one example. Say page 4. Example. Imagine you're holding like a cold block, which is made of either aluminum or concrete, infinitely, semi-infinitely long, at 23 centigrade Kelvin, and this is your palm. Okay, at 37 degrees centigrade body temperature. And the question is the following. So this is block, like cold block, and it's either aluminum or concrete. Okay. In which case aluminum or concrete would your palm feel colder? Palm feel colder. So one thing important is our body does not differentiate the temperatures, but it differentiates the temperature fluxes. Our skin is sensitive to heat fluxes, not the exact temperatures. You can actually do this experiment. You can actually put your hand, you can have like a cold water bath, a hot water bath. You can put both hands on two sides, one hot, one cold, and then you will also have one warm, like a medium temperature. But please don't actually burn your hands. Just work with a like comfortably warm enough temperature for the hot. So you put one hand goes into warm, one hand goes into cold, and then you just wait for 1 minute or so, and then you put both of your hands. You take out both of your hands and put both in the medium temperature water bath, and then you're gonna feel as if you're gonna feel colder on one hand that was staying in the warmer one, and you're gonna feel hotter with the hand that were in the colder bath. This is because if your hand is colder, the flux is gonna be larger, so it's gonna feel hotter. If your hand was warmer in the previous case, then the flux is gonna be less, then you're gonna feel cold. You're gonna feel cold. So so long story short, you can do this experiment and convince yourself that your skin is sensitive to heat fluxes rather than the exact temperatures. So to answer this question, we need to compare heat fluxes in the two cases, right? Okay. So the heat flux Q is equal to minus K times del T over del X at X is equal to 0, right? So this is a semi-infinite case, and I take my X is equal to 0 here. And that's equal to minus K times del T, basically it's dt dt over d combined variable eta times d del eta over del x, and you estimate this at eta is equal to 0, and you estimate this at x is equal to 0. And since eta, you know, that is equal to x over 2 square root of alpha t, del eta over del x is equal to 1 over 2 square root of alpha t, right? And yeah, so this becomes equal to, yep, so we need to find also del t over del eta, right? And we found that the t was equal to, oops, maybe we should write t minus t0, t minus ts divided by t0 minus ts is equal to error function eta. Or in other words, 2 over square root of pi integral from 0 to eta exponential minus eta squared d eta. Okay? And thus, from here, dt over d eta is equal to 2 over square root of pi. Well, actually, you also have, I'm sorry, 1 over t0 minus ts, because I would like to take the derivative of both sides. And derivative of this thing is derivative of t divided by this constant number is equal to 2 over square root of pi. And the derivative of the integral from the fundamental theorem of calculus is the derivative, sorry, the argument of the integral estimated at the boundaries. So this is basically exponential minus eta squared. Okay. Good. Okay. So dt over d eta at eta is equal to 0 comes out to be t0 minus ts 2 over square root of pi times exponential 0, which is 1. And then you plug in this thing here, and you plug in this thing here to get q is equal to minus k t0 minus ts 2 over square root of pi 1 over 2 square root of alpha t. 2's cancel, and you get q is equal to, okay, t0 ts. If you like change the order of t0 and ts, you get k times ts minus t0 divided by square root of pi alpha t. Okay. Good. Any questions so far? No? Okay. So you can also play with the alpha. You know that the alpha is basically k over rho cp. From here, you get basically ts minus t0 divided by square root of pi t square root of rho cp k. for the material. So if rho CPK is larger, then it means you have a larger flux. It means you feel colder. So let's see which one is larger for which material. So typical values of rho Cp, K, rho, and Cp. K is what per meter Kelvin. Rho is kilogram per meter cube. And Cp is joules per gram centigrade. You can convert it to kilogram centigrade, but it doesn't matter. We're going to make a comparison, not going to make quantitative estimation. Aluminum and concrete. So here are the values: 205, 0.8, 2700, 2400, 0.9, 0.9. So I'm wrapping up very quick, don't worry. And so the Q aluminum divided by Q concrete, you find that it's going to be the ratio of the square root of those numbers. Rho aluminum, K aluminum, Cp aluminum, divided by rho concrete, K concrete, Cp concrete. And let's plug in the numbers. 205. So let's go in order. 2700, 205, 0.9. Cp and rho are almost the same, but the K is much larger for the aluminum. That's why we're going to get a value larger than 1. Which is equal to, approximately equal to 17, which means that aluminum block will feel colder. That's independent of time, because you see the times cancel at any time. The Q for the copper, Q for the aluminum is going to be larger than the Q for the concrete. Okay, so that's an example that we applied what we learned so far.